Thank you very much for giving us the opportunity to present here. So I will talk about some work that we've done along the eastern coast of the Philippines a few years back in collaboration with Arnold Gordon. So this is part of a program called OKMC, or Origin of the Curusio and Mindanao Current. So So here we have if you look at the Western Pacific, the Philippines is on the western edge of both the North Pacific subtropical gyre and the tropical gyre. So it receives the North Equatorial Current, and just off the coast of the Philippines, the North Equatorial Current bifurcates and supplies the Curusio and also the Mindanao Current to the south. So it's a very important region where where it forms the origins of both the Curusio and the Mindanao Current, and it also partitions the transport and the heat, particularly the heat transport between the subtropical gyre and the tropical gyre. So in 2011-2012, we did a couple of cruises during the summer season, and to try to look at this area here. This is the bathymetry of the eastern coast of Luzon. So east of Luzon, you have a very narrow shelf, and then in the southern part, you have a very wide shelf here, about 100 kilometers at its widest point. And then south of that, again, you have a very narrow shelf. So the shelf here is very interesting because of this promontory here, this bump in the shelf configuration. And so it is just off here that the North Equatorial Current reaches the Philippines, but the North Equatorial Current also shifts in position depending on season, depending on other factors like ENSO events. So the NEC actually varies position from roughly around here to around 10 degrees north. And we were fortunate that we made cruises in the summer of 2011, 2012. We were only focusing on this area here, but two events, serendipitous events made us move south. So in 2011, we had to run away from a typhoon. So we had to move south, and during that southward movement, we were able to capture where the NEC bifurcated. And in 2012, the ship was coming from Australia, so on the way up to this area, we were again able to measure where the bifurcation occurred. So in 2011, the bifurcation was to the north, and in 2012, it was to the south. And this affected the properties of the water here. When the bifurcation is to the south, most of the water that's being supplied to the Curusio is more tropical waters from the NEC, while when the bifurcation is to the north, most of the NEC water moves to the Mindanao Current, and most of the water here comes from essentially subtropical waters recirculating from the from the north. So as you can see here, this is average chlorophyll. To the east of the Philippines, you have very low chlorophyll, very oligotrophic waters, very clear waters. And we wanted to see also whether there was, we could also see from the chlorophyll data this change in properties because of the shift in the position of the NEC. And these are interpolated currents from the underway ADCP, the hull-mounted ADCP from the ship, interpolated. Here we have the 2011 and 2012 surface velocity fields. This is roughly at around 20 meters. And you can see the Kurushu here. Kurushu becomes a real western boundary current at around 16.5 degrees, because from the NEC it moves north. At this point we call it the nascent Kurushu. It's not yet a real western boundary current. It only forms at around this latitude. The shelf promontory I showed earlier actually is where that northward branch separates from the coast and moves towards this position. And as a result, it forms this cyclonic eddy on the inshore side of the Kurushu. And this cyclonic eddy is actually very persistent. We've seen it every time we go there, we see features of this cyclonic eddy. The vectors are color-coded with chlorophyll, and here we can see that chlorophyll in 2012 is lower compared to 2011. 2012 is mostly NEC waters. 2011 is recirculation from the north. So there's a strong relationship between the properties of the water in east of Luzon with the bifurcation latitude. We wanted to see over the 20-year period, a paper by Chu and Chen, they showed that the bifurcation latitude of the NEC is actually shifting to the south over the last 20 years. And so if we plot the sea surface height anomaly at this point here, this is roughly the position of the Benham Bank. The solid line is the bifurcation latitude, and the dashed line is the sea surface height anomaly, and you can see an inverse relationship between the bifurcation latitude and sea surface height anomaly. So in the tropics, you can make use of the sea surface height anomaly as a proxy for temperature. So higher sea surface height anomaly, warmer waters. And so over the 20-year period, we also see a slight warming of SST east of the Philippines. And that relationship between the sea surface height anomaly and the bifurcation latitude spreads all over the eastern coast of the Philippines. So also here we can see some of the seasonal variations of the bifurcation latitude and also some of the ENSO effects. And it's very strong relationship between sea surface height anomaly, or SST, and bifurcation latitude. So when the bifurcation latitude is to the south, you have the warmer waters entering the east of Luzon. These are the warmer waters coming from the north equatorial current. So even in chlorophyll, this is mode 1 of the EOF of monthly chlorophyll from 2003 to 2015. You can see that offshore of the Kurushu, we have also a strong relationship with NEC bifurcation latitude, which is this black line. Red line is mode 1. So when the bifurcation latitude is to the north, you get less tropical NEC waters, so you have higher chlorophyll, and vice versa. What is also interesting is on the inshore edge of the Kurusho, you have very high chlorophyll, and its variation appears to be opposite that of the offshore waters. And this is probably a result of the interaction between the Kurusho. When it is strong, you get higher chlorophyll. When the Kurusho is strong, you get stronger interaction with the shelf. You get dynamic uplift and higher chlorophyll. These are snapshots of chlorophyll in 2011, roughly when we had those cruises. And you can see this, you can trace the inshore edge of the Kurusho based on this sharp gradient with chlorophyll. And here you can see this pattern of the cyclonic eddy on the inshore edge of the Kurusho. So aside from looking at the variability of the transport of the Kurusho and the Mindanao Current and the NEC, we're also interested in looking at the influence of eddies on the western side of the Philippines. This is a eddy variability map in a paper by Chu and Chen. And between Taiwan and Luzon, we have this area which is very rich in eddies. This is where we have the subtropical countercurrent. So part of the flow of the Kurusho, some of it branches towards the east and moves towards the east here, but below it is still the north equatorial current. So this strong shear is creating a lot of these eddies. So this is a very rich in eddies. This is we used eddy detecting algorithm on Cesar phase height anomaly, and this is an animation. And we can see this. Most of these eddies are generated here, east of Luzon Strait, and it's all moving westward. And the area of the Benham, or the east of Luzon, is at the southern boundary of these eddies. So there are times when the eddies are further north, and there are also times when the eddies are further south. And these eddies are actually influencing the transport of the Kurusho. When these counter cyclonic or anticyclonic eddies impinge on the Kurusho, it changes its transport. So when we have a cyclonic eddy hitting impinging on the Kurusho, the transport of the Kurusho actually decreases. When we have an anticyclonic eddy hitting the Kurusho, the transport increases. So these are from papers by Renchi and Lee. And so they are a source of variability in this area here. This is also another example. When we did the 2011 cruise, we put up a mooring in the Benham Bank. At 170 meters, we had a temperature sensor, and we retrieved the mooring a year after, so we have this time series. And we can see this very strong oscillation of temperature, roughly with the period about a month. But it disappeared towards the end of the year, and in 2012, the temperature just increased. And so we overlaid this with data from sea surface height, sea surface topography data, And, oh, sorry. So we can see when you have these oscillations are actually associated with eddies which propagate through this area. And this occurred in 2011. It weakened towards the end of the year, and when if we just so we can see some of these eddies passing through. But when 2012 started, when temperature started to increase, we can actually see that the area was just swamped with warm waters coming from the NEC. So most of the eddies were shifted further to the north. And this is also another picture of those propagating eddies. This is longitude here. This is the end time from 2011 to 2012 along this transect. And you can see the slopes are westward, so it shows you the westward propagating eddies. But starting 2012, we can see this warm water inundating the area. So most of the work we've looked at has been focused on the northern branch of the NEC. We don't have a lot of information on the southern, the Mindanao current part, so we're very excited also to work with Dr. Lee, who's proposing a cruise also on east of Mindanao within the year. Our other research interest, now we're looking at the air-sea interaction program in Western Luzon. This is summer monsoon rainfall at 3-hour intervals. No? So this is 2 o'clock in the morning, 5 o'clock in the morning, 8, 11, 2 and 5 in the afternoon, etc. So you can see that there is a very strong diurnal cycle in precipitation in Western Luzon. At 5 p.m., you get a lot of rainfall over Luzon, but at 2 a.m., you can see that most of that rainfall falls over the ocean. And that's over a scale of about 200 kilometers. So that's a strong diurnal cycle. And we're also planning to conduct some field experiments in 2018, summer monsoon of 2018, and try to see what the influence of the upper ocean is on this cycle as well. So I think I'll end here, and thank you very much.
So we have a plenty of time to receive the comment or question.
Thank you very much. If I remember correctly, your bifurcation latitude looks like moving southward with times. What will be the major dynamic or some regions? You show that your bifurcation of western bound currently moves southward with time.
Yeah.
So what is the major region for that?
Well, the paper doesn't mention it. They think it's a larger scale change maybe in the wind patterns, but it's hard to attribute it to climate change. But definitely it's a long period oscillation. We're not sure if it will continue moving to the south or it will undergo another oscillation.
Okay, so any other comment or question? Okay, thank you.